and that you're going to like this. Hello and welcome back to Calculus 1, section 5.2, the definite integral. So we are going to look now at the definite integral, its definition, right, where it comes from. And we start with the idea that we already covered in 5.1, where we had a function, and we said from A to B, and we said that we partition and we had some n number of rectangles, and we do left to right sum. And then we said for the greater precision we put in even more rectangles, and if we are not happy with that, what do? More rectangles. We do even more. And if you are not happy with that, what do? Even more rectangles. Great. I got this. Don't worry, I'm a professional. Don't worry, you will compute only one example. If you're not happy with this, what do? Even more rectangles. But you know what I'm going to do? I'm just going to color it like this now. Because, do you know how many rectangles I actually put in right now? Infinitely many, exactly. So what I have done here is I started with 4, and then we said let's add double amount to 8, and then 16, 32, 64. 128, 256, 512, 1024, 2048, 4048, and so on. So it goes on and on and on and on, right? But then, all of those are approximations. What I'm going to do is to get exact area. So, the 5.1 section was considering 4 or 5 or whatever number of rectangles, and this section now is going to consider infinitely many, because that fills all of the space, no error, no rectangles. Each rectangle is what thickness now? What is the thickness of each rectangle? What is the thickness of each rectangle?
Almost 0.
Almost 0. The thickness of each rectangle is going to 0. So, if you look at this, my delta x, which is always the formula b minus a over n, is actually going to 0 because n is going to infinity. So these rectangles are infinitely thin, and they're all crammed next to each other, and since they technically have no width, they cover all of the space, and they touch the function at exactly one point. Therefore, there is no room to create a little rectangle to get the area or the error. So we are going to get the exact with this. Now, please observe the way I build the formula so you're not confused later. You should be looking at the screen, not in your notebooks now. I'll do this twice. I'll use f of ci. I create a single area first. So, guys, look at the screen. I create the single area first. Then I add all of those areas from 1 to to n, sorry. So, how many I have? And then I send that n to infinity. That's how we built this. I'll do it again from scratch. So, I start with the function times delta x for a single rectangle. Then I add all of the rectangles from 1 to n that I have. If I have 1 or 2 or 5 or 8, whatever I have them, I add them. And then I said, well, you know what? Instead of using a finite number of them, n, let me send that n to infinity to say that I have infinitely many. This is going to give us the exact area. This is called Riemann Sum by mathematician, German mathematician Riemann, who figured this stuff out in 1800s. So welcome to being about 200 years behind current mathematics. So this is the formula which calculates exact area under the curve. So let's use it to compute say area under f of x equals, well, do two examples. So 2x minus 1 on interval, let's go 2 to 5. So I'm not giving you n equals 5, n equals 8, or anything like that, because we are to use infinitely many of these now. All right? Well, we'll have to think a little bit to get these. So, what do I have? Well, I have this line, and I have my region that I'm considering. So yeah, we can go and do the geometry and get it because it's a trapezoid, so easy. But let's say we don't know how. So I'm going to put few rectangles here. Obviously, first value is a, which is 2, last value is b, which is 5. And I can calculate delta x as b minus a over n, which is 5 minus 2 over n, which is 3 over n. Since I don't have n, right, I have to leave my delta x as 3 over n. And you know what? I'm happy that I have this 3 over n as delta x because that's one of the building blocks of my formula. So now we have what delta x is, 3 over n. The next question is, how much are each of these points here on the line on x? Because that sequence of points is that CI sequence inside the f. You will be computing f here, and here, and here, and here, right? So you'll be computing f at all of those points. So you need these points from the bottom. Well, this CI business is, should I say obviously, if you look at the picture, a plus I times delta x. I is the counter. So, what does this mean? Well, when everything starts, it starts with I being equal to 0. So, the first CI, the first location where you compute the function is going to be at A. And then when I is equal to 1, you see that you are getting, if I zoom in, you see that this is delta x and delta x and delta x. So I hope that you see that C0 is A, C1 is A plus delta x, C2 is A plus 2 delta x, C3 is A plus 3 delta x, going forever. So this is a formula. And I know what A and delta x are. So I have that Ci is equal to 2 plus 3 over n times I. Please do not confuse this I with the complex I. It has nothing to do with it. I is a counter. So now I have this. I have delta x and I have Ci. I need to create f of Ci. Well, f is given to me as 2x minus 1. So that's 2 times 2 plus 3 over ni minus 1. So now I have 4 plus 3 over, 6 over n I minus 1. And finally f of Ci is equal to 3 plus 6 over ni. Now if I look at my formula for exact area, from 0 to n, 1 to n, f of Ci, well, let me write it, it's f of Ci delta x. We have everything to plug in now. Limit, n goes to infinity, summation 1 to infinity, f of Ci is given as 3 plus 6 over ni, and all of that times 3 over n, which is delta x. This formula will be different every time because we calculate everything from scratch every single time. Your delta x depends on values of a and b, so as soon as I give you different interval than 2 and 5, this changes into a different value. Again, the formula for Ci is the one boxed in red. Maybe I should box the formula for delta x in red as well. So formula for Ci is boxed in red, but then with a different value of a, you are going to have different values of a and delta x. So that changes every time. And then with a different function, f of Ci changes every time. So this is like a triple deal that you have to compute from scratch every time you see a problem. You compute delta x first, then you compute Ci, then f of Ci, and then you are able to plug everything into the Riemann sum. And this is where fun begins. To solve this now, we start with the limit, n goes to infinity, summation 1 to infinity, and what you have over here is
too much fun.
I knew this was gonna, every time I get excited about a concept, this program immediately checks out. I think it senses my level of the excitement in the voice, and then it says, nah.
It's just getting too excited as well.
Yeah, but you should be excited and work, not quit. So 9 over n plus 18 over n squared I when you distribute everything. How do we take the limit of a sum? Well, these are the formulas that I did not talk about earlier. You see, we cannot take the limit of the sum because the sum has the counter I equals to 1. Now, what's important to realize here, that in the eyes of the sum, I is the variable, and n is a constant, and in the eyes of the limit, I is the constant, and n is the variable, right? And you have both of these applied to this parenthesis of 9 over n plus 18 over n squared I. So what do we do? Well, what we do is we split this into two sums, and we use formulas to convert sums into algebraic expressions with n's. These are called sum of powers of integers, and they're given on a page 340. So I'll show you those formulas briefly. They're in the box, and you see the summation of a constant is Cn, summation of the k, I use I, they use k. Summation of k is n plus 1 over 2, and then k squared and k cubed. You have those four formulas. So that's actually, in our language, it's going to be C, I squared, and I cubed. So those are the formulas. They're in the textbook, and we are going to use these formulas to transform the summation on the left-hand side into a non-summation on the right-hand side. And it appears that you are writing these formulas down, so I'm going to wait. Even though this isn't a textbook and it's supposed to be on your class prep on 5.1. I'm not sure why you're writing these, but whatever. I'll wait. It's okay. I'll wait. So the first one is summation of C of a constant is equal to Cn. So that constant, whatever. So summation of 3 is 3n. Summation of 7 is 7n. The second one is summation, and in our case I. So it's just going to be n plus 1 over 2. The next one is I squared. A squared is n plus 1, 2n plus 1 over 6. And then I cubed, n squared, n plus 1 squared over 4. So those are the formulas that we have. And now let's go and take care of the algebra. So what do? We start with the limit. N goes to infinity. And now we're having a summation. I goes from 1 to infinity. I should say to n. To n, not to infinity. Of 9 over n plus another summation 18 over n squared I. Again, 1 to n. So what I've done here is I split one sum into two separate sums. We know that we can do that because sum is a summation, it's addition, and that's addition in between, so we can just split apart and make two additions. Again, limit n goes to infinity. All right. See this n. N is a constant in the eyes of the sum because the variable is I. So I can kick 1 over n outside and leave this as a summation of 9. Plus, and the same thing happens on the other one. I'm kicking out 18 over n squared, and I'm just leaving I so we can apply the formula. Those formulas that you put on your class preps. I know. So now I have 1 over n, and then this is going to be 9n. That's what it is. And you know what? I'm just going to say like that, and I say formula. There we go. Plus 18 over n squared, and then for I, we have n plus 1 over 2. And then I'm going to circle those and say formula. There we go. And now follow algebra. Limit n goes to infinity. N and n cancel. 9 plus 18 and 2 cancel. 9 and one of the n's cancel. You have n plus 1 over n. 18. Because the limit of n over n is 1. 1 times 9 is 9, so 9 plus 9 is 18. So it seems that the area under the curve is 18. Now if you are to draw this on a graph paper carefully with the ruler and stuff, and then you count the number of squares, it has to be 18 squares when you fit everything together. The procedure is highly structural. These are steps, and they're always the same. You start from figuring out delta x, because delta x is used to figure out CI, and CI is used to figure out f of CI. And then when you have f of CI, it's f of CI times delta x within a sum within a limit. Distribute, split sums, apply formulas, and do the limit. 1, 2, 3, 4, 5, 6, 7 steps. Let's do another example. Exactly.
So is that going to be the exact answer?
That's exact answer.
Okay, that's the most precise.
Here in blood. We used infinitely many. You see this? That sends number of rectangles to infinity. We used infinitely many rectangles. So that value that we got there is exact. Let's jump one step further. So find the area of, let's say, f of x equals to x squared minus x plus 3 on 3 to what? 3 to 8. Thank you. I couldn't remember any of the numbers. All right. We do the same procedure from scratch. Here, formula. Delta x is equal to b minus a over n. In our case, 8 minus 3 over n, which is 5 over n. So delta x is 5 over n. Formula. Ci is equal to a plus I delta x. In our case, a is 3 plus I times 5 over n. So Ci is equal to 3 plus 5 over n I. And then we need to compute f of Ci. Compile f of Ci. Well, f is given as x squared minus x plus 3. So the Ci goes for each x. So I have 3 plus 5 over ni squared minus 3 plus 5 over ni plus 3. Well, there is some algebra to be done here. Lots of it, right? Lots and lots of it. So square the first one. That's going to be 9 plus 30 over n I plus 25 over n squared I squared. So that's all, as you can see, all of that is squaring the first one. Then we have minus 3 plus 5 over ni, and then plus 3. And then these guys die. And I get to add like terms. So the final answer over here, and I'll put it in a descending order. So 25 over n squared I squared first. Then plus 35 over n I second. And then plus 9.
If you just follow the negative sign, so isn't it going to be negative 5 over n I?
Oh, yes, you're right. I completely... Yes, so that's a 25, not 35. Thank you. That will actually ruin everything. Nice. So it's 25i. Yes, it's a negative. That negative distributes. Great. So now I have f of ci. I will write the Riemann formula again. Exact area is equal to the limit n goes to infinity. Summation of 1 to n. And then over here we have f of ci times delta x. That's the formula. Plug everything in. A is equal to the limit n goes to infinity. Summation 1 to n. In parentheses I have 25 over n squared I squared plus 25 over ni plus 9, all of that times 5 over n, which is delta x. Distribute, split sums, use the formulas, do the limit, be done. Distribute 125 over n cubed I squared plus 125 over n squared I plus 45 over n when I distribute 5 over n to each. Time to split into 3 sums. Summation, I keep putting infinity, 1 to n, 1 to n of 125 over n cubed I squared plus summation 1 to n 125 over n squared I plus summation 1 to n of 45 over n. In order for us to use the formulas, we have to get rid of all of the non-I terms. Over here we'll just get rid of the n because we have a constant 45, so we can use the formula for a constant. I mean, you can technically kick everything out and leave 1 and then just say n, which gives you the same. So now the next step, we kick all of those non-I terms out. So 125 over n cubed, summation 1 to n I squared, plus 125 over n squared, summation 1 to n of I, plus 1 over n, summation of 45. And now use the formulas. So 125 over n cubed, copy, and I squared is given as n plus 1, 2n plus 1 over 6. Plus 125 over n squared, and then n plus 1 over 2. And finally, plus 1 over n times 45n. So that's just a formula. Limit n goes to infinity. All right, now you're supposed to take these limits. What matters is only the highest exponent. You know, when you're taking the limit to infinity, you only look at the highest exponent on top and the highest exponent on the bottom in the denominator. If top is larger, the limit is infinity. If bottom is larger, limit is 0. If they have the same exponent, it's a ratio of front coefficients. I understand it will take time to distribute this, but we don't have to. You only need to distribute the first ones. So what you have is n times 2n, and everything else will have a lesser power. So we don't care about anything else. We only care about the front coefficients. So that's going to be 250 over n cubed over n cubed, sorry, 6n cubed, and the rest we don't care about. Plus 125 n squared over 2n squared, and finally plus 45. So the limit kills everything else. Everything else goes to 0. These are the only ones that survive. And now all of these n's cancel as well. Boom, boom, boom. And what we have is the exact area is 250 over 6 plus 125 over 2 plus 45. So now you can punch that into your calculator. And get 149 and 1/6. Which is as improper 895 over 6. That's exact area. I mean, if there were no calculation errors, that's the exact area. Please, next time someone tells you, what do you know? Work this out on a napkin.
Where do you go that have napkins this big? Like, what magical bar are you at that have, like, napkins that are like this?
Well, we can skip some steps. Tell them that there are 3 napkins of steps in between. All right. So, let's try something else. Integral (2x minus 1) dx from 2 to 5. What is the integral of 2x? Well, it's x squared and it's minus x. That's the integral. The antiderivative from 4.9. You had this on your exam. I expect you to know that. And instead of putting plus c, I'm going to put this vertical line, which means compute between 2 and 5. And now I'm going to plug in 5 and then subtract, plug in 2. So this is 25 minus 5 minus 4 plus 2. That's 20 minus 2 is equal to 18. Should we do the eye doctor exam? What's better, A or B? No, B is better. So it appears that your 4.9 with this extra calculation piece over here gives you the thing. Cool, right? Let's try something else. So that's x cubed over 3 minus x squared over 2 plus 3x if I use 4.9, and I need to compute from 3 to 8. I'm going to plug in 8 first, so that's 8 cubed over 3 minus 8 squared over 2 plus 24, I can do that, minus, and now plug in 3. 3 cubed over 3 minus 9 halves plus 9. So I plug in the top number first and then the lower number. Alright, so what do I have? I have 8 cubed. So that's a 64 times 2, 128, 256, 512. Over 3 minus 64 over 2 plus 24 minus one of the 3 is cancelled, so this is just a 9, so minus 9 plus 9 halves and then minus another 9. So that's 512 over 3. Now minus 64 and plus 9, that's going to be 64 minus 9 is 55, so minus 55 over 2. And then 24 minus 18 is 6, so plus 6. The common denominator here is 6. So 512 times 2 is 1024. Minus 55 times 3 is 165. And then plus 36. So that's 1024 minus 165 plus 36 is equal to 895 over 6. Should we do eye doctor exam on this one? What's better, A or B? So now you have a choice. You're either going to learn the antiderivatives and then compute the exact area using integrals, or you can use this method here, which clearly works. A or B? B. Exactly. So we see that these calculations are equivalent. What you've seen me calculate here is something that is called the definite integral. And the definite integral computes area under the curve. So first we say integral a to b of f of x dx is equal to the antiderivative capital F of x computed from a to b, which is f of b minus f of a. So that's the definite integral. Now we have to be careful because the definite integral doesn't give us exactly area under the curve every time. It gives us the net area. And we have to be very careful about that. So there are some properties that are really cool. For instance, a property a to a of f of x dx is 0. Why? Very good. I'm not computing any area. There's no object. Your object is defined between A and B. Well, if you only have A and A, that object has a 0 width, therefore 0 area. That should be common sense. There is another cool feature which says that the integral AB f of x dx can be broken into multiple integrals. So a to c f of x dx plus c to b f of x dx. Now this needs to make sense immediately when I draw the picture. I pick value c somewhere. It doesn't matter where I pick it. The total area between A and B must be the sum AC, C to B. Do we all see that? So don't make that something crazy. It is any interval 3 to 5. You can go 3 to 4 and then 4 to 5. Or you can go 3 to pi and then pi to 5. Whatever you break it. It doesn't matter where you break it. It doesn't have to be in half. So if you have same numbers, here, then the integral is 0. You can break them apart anywhere. And there is this other cute formula which says that the integral a to b of f of x dx is the same as negative integral b to a f of x dx. So if you swap the limits, you put the lower limit up and upper limit down, the integral picks up the minus sign. That should be also common sense, because this side is going to be f of b minus f of a, and this side would be negative f of a minus f of b, and when you distribute the sign, you get the same sides, right? You get the same on both sides. That's a proof for those of you interested in proofs. So these are the 3 formulas that you need to know for definite integrals. Now, I need to stress this formula for now, and we will stress the second formula for Calc 2. But this formula in the middle is crucial for your correct area calculations in Calculus 1, and then obviously your engineering, physics, and everything else. Integral is the area under the curve, could be energy. So you have to compute that in physics. There we go. So let's paint a picture. You are tutoring someone, 7th grade, and you're making millions right there. And area of the triangle came up. This is 3. And this is 5. So, what is the area under the curve? What is the area under the curve? Well, obviously you will say area is equal to 1/2 3 times 5, right? Well, 5 times 3, whatever. It's 15 halves. And then the kid goes, Why? Ooh. Let me show you why. Sleeves up, and then you say, I have a function over here, f of x, which is equal to negative 3/5 x plus 3, because that's the area of the, that's the slope is negative 3/5, right? The y-intercept is at 3, so function is a linear line. And then you say area is equal to the definite integral, 0 to 5, right? That's your base, of negative 3/5 x plus 3 dx, right? And then you integrate this. So negative 3/5 is a constant, you copy that. You have x squared over 2, integral of x, plus 3x computed from 0 to 5. This turns into negative 3/5, 25 over 2 plus 15 minus 0 when you plug in zeros. And now this works out to be negative 75 over 10 plus 15, which is 75 over 10, which is 7.5, which is actually 15 over 2. That's why. And it automatically becomes clear. You can't be more clear than that. Definite integrals compute area under the curve. So when they ask why, you know why. Now we're going to ask you in the future why. That's a different story. But for that one time, you covered. I know you love trig. So what's the area? Find the area under y equals sine x on 0 to 2 pi. You know what to do. Plug in sine into integral. You have the limits. Integrate, plug in, compute. So that will be plenty of time for you to find the answer that you really don't want to see, right? What'd you find? 0. And you know that the area under the sine curve is not 0, right? What? Yep. So when you draw the sine curve, you clearly have place to color. That means there is area, right? But then your integral said 0. Well, the reason is that the top part and the bottom part are exactly the same, and the top part creates positive and the bottom creates negative for the net area to be 0. So we have to battle that. 0 to 2 pi, and at pi we have to cut there. And that's why we need that formula where I said that your integral can be cut anywhere and you compute two separate ones. So the integral 0 to 2 pi of sine x delta x is going to be cut into 0 to pi sine x dx, which is the first bump on the positive side, plus the absolute value of pi to 2 pi sine x dx for the second part. Now, it's not always going to be symmetric, so you actually will have to compute both of these most of the time. I'll give you an example of the x cubed graph that does this. So clearly, the area here is not going to compensate or be the same as the one there. So you are going to have some net area, but it's not going to be actual area because it will be that minus the part. So you have to be careful about those things. But we'll deal with that. What's the integral of sine? Very good. Negative cosine from 0 to pi plus absolute value of negative cosine of x from pi to 2 pi. So now you have negative cosine pi minus negative cosine of 0. Remember that there is a minus in the formula. It's f of b minus f of a. So this is the f of b minus f of a. That's that minus. And then cosine has its own minus.
But you put that in absolute value.
That's plus absolute value negative cosine of 2 pi minus negative cosine of pi. Bueno? So this is your f of a, f of b minus f of a, and then f of b, f of a. So we have all of those. We go and we say negative cosine of pi. Negative cosine of pi is 1 because it's negative, negative 1. Minus cosine of 0 is 1, so you have another negative 1 there. Plus absolute value, cosine of 2 pi is 1, so it's negative 1. And then minus cosine of pi is negative 1, so it's another 1 there. So this is 1 plus absolute value of negative 2, altogether 4. Please, someone comment on how cool is it that the area under this curved sine graph is 4. It's not 4 pi, it's not half a pi, it's not pi cubed or anything like that, it's just 4. Which is great. So these are some of the things that you have to, be careful about. So, is the definite integral necessarily equal to area? And the answer is hell no. It's the net area. And you have to be careful and notice when the function dips below x-axis. Anytime the function dips below x-axis, it will create that minus area, which would be creating. Now, that's good that it's happening, because we do want to know about positive energy and negative energy and voltage drops and all of these kind of things that the integrals are used for. I'm not saying that that's bad. Far from it. That's awesome. It's just that we have to be careful, because there is a whole spiel of application that depends on computing these correctly. So if you are talking about the energy as a potential energy now and zero kinetic energy, as I let go, it will start losing potential energy and gaining kinetic energy as it accelerates on its way down. Now, you might know those from the formulas that you learned in physics, right? Where the kinetic energy is 1/2 mv squared. Kinetic energy depends on velocity, speed, and then as something that you drop due to acceleration of gravity, it will be changing the speed, therefore accumulating more kinetic energy. Where your potential energy, mgh, is the energy that depends on the height. Well, as something is dropped, the height is getting smaller, so potential energy is smaller, kinetic energy is on the rise, for the total of energy, which we call conservation of energy, to have it. And now what we're going to do, in physics, you are going to hit some integrals around. You're going to have, depending on how deep you go in your physics courses, some of this stuff will be covered in calculus later on, and you can calculate those energies using integrals. The last thing that I want to say for 2 minutes is the second half of the story on kinematics of motion, where we know that we started with a position function s of t differentiated in time to get velocity, differentiated in respect to time to get acceleration. Now we can finally integrate in respect to time to go from acceleration into velocity, and again integrate in respect to time to get back to position. Now, this has huge implications, because if you start with your acceleration, which was the change of velocity, v prime, and that is, let's say, gravity g as you throw something. When you integrate both sides, you get that the velocity, right, if I integrate both sides in respect to time, you get that the velocity is equal to gt plus some constant c, and I'm going to call that constant c initial velocity v0. Because when you plug in t equals 0 at the beginning of time, that kills g and you just have v0, right? You've seen this formula in your physics class. You know that the velocity final is equal to velocity initial plus acceleration times time. Now, if I'm a little bit clever over here, I put negative g because it's pulling down, you get this type of equation. And then you realize that the velocity is the derivative of the position, and you have your negative gt plus v0, and you integrate now both sides in respect to time. You get another formula that you are forced to memorize in physics, where s in time, or height, or whatever, is equal to negative gt squared over 2, well, 1/2 gt squared, plus v0t plus s0 initial position for parabolic motion. And you can see it's a parabolic motion. There's your negative x squared, negative t squared on a t-axis. Right there. Parabolic motion. So we're finally done with getting these things, concepts together, limits, derivatives, integrals. The next section, so we will be done with the material next week. The next lecture is Fundamental Theorem of Calculus, which will tie all of this together, and then after that we can do a little bit more work with formulas, and then focus on integration techniques after that, which leads into Calc 2, along with application. See you all in a week.